Let's look at one of the simplest data structures which exists today. And this data structure is known as a linked list. So linked list is a data structure in which each element is linked to the next. In a simple linked list, the only way to access the nth element is by traversing the first n-1 elements. And why we say simple linked list? Because at times what can happen is that in a certain kind of implementation, the data structure might be augmented and you may be able to do something much more faster than accessing the first n-1 elements. So this is shown pictorially here. We have a start pointer which points to node 0, where node 0 is the beginning of the linked list. Then node 0 contains another pointer which points to node 1 and so on. The last pointer typically is going to point to a null element, or that is NULL in C, which is 0x0 ASCII, or we can have certain other mechanisms of denoting that this is the end of the linked list. So what you must note is that there is only one pointer which is pointing, and the space requirement of such a linked list is basically pointer storage for each node along with the data. So if in case your data is an integer, then the pointer also on most of the platforms are going to have the same kind of a storage requirement. And what is going to happen is that your storage will actually be 2n, where n is the number of nodes in the linked list. A small augmentation to the singly linked list is that of the doubly linked list. So in case of a doubly linked list, each node also points to the previous node. So as shown here. So we have the start pointer pointing to node 0, and it contains another pointer which points to node 1. Also node 1 contains a pointer which points to node 0. So the advantage of our doubly linked list is that it's very easy to move in both the directions. That is from beginning to end or from end to beginning, as well as from each node you can always go back to the previous node, which is not the case when you are using a singly linked list. So what we have also shown here is the R start or R end, which stand for reverse start or reverse end. And this is a common notation which will be used once we look at the STL implementation of the list. Of course, in case of doubly linked list, the memory usage increases because now we actually have 2 pointers per node. So if we are storing an integer with each of the nodes, then the total memory requirement is going to be 3n, because we also have 2 pointers there, where n is the number of elements. So singly linked lists are the most popular in literature because of the low overhead, and more often than not the linked lists are used in places where the overhead is expected to be low, or where you want to keep the overhead low, and there is no need to do a random access, because random access on linked list is going to prove to be very expensive. Another advantage of linked list is that they make efficient use of the memory space of the system. So remember what I had been mentioning, that your system may have just say a total of 1 GB memory, and you try to allocate 600 MB memory together. Now the system may not be able to find the 600 MB in one go, because it is possible that it does not have a contiguous chunk of 600 MB memory. Whereas it might have 600 MB available in various small sizes, that is say 100, 100, 200, 200 or 300, 300 kind of a chunks. So the advantage with linked list is, since each of the memory for each of the nodes is allocated when we are trying to create the node, the linked list can make efficient use of this fragmented or distributed memory, and you will still be able to create a data structure which requires 600 MB memory, which is not going to happen if you are actually trying to allocate a contiguous storage or an array. So let us look concretely at what are the operations which are efficiently supported on a linked list. One is the traversal. So in case of a traversal, the lists are easily traversed from the beginning or the end, if it is a doubly linked list, in O(n) steps, where n is the total number of elements in the linked list. One of the advantages of using a linked list is the easy insertion as well as deletion. So elements are inserted at the front or at the end in case of a doubly linked list in O(n) steps, that's constant time. also given a pointer to any node in the linked list, again the new element can be added just after or before, provided it's a doubly linked list in constant time, that is O1 steps. So insertion is one of the strong points of linked list. Another strong point is that of a deletion, that given a pointer to the node which needs to be deleted, it can actually be done in constant steps. Size. So size operation in vanilla list is expensive. Why? Because if the data structure is not storing the total number of elements in the linked list together, then what needs to be done is that you basically have to traverse all the elements in the linked list from beginning to the end, just to calculate the total number of elements in the linked list. And this is going to take O(n) steps, where n is the total number of elements. However, a slightly modified implementation of the linked list can store the number of elements in the linked list at one place, and then it becomes a constant time operation. Is empty, to find whether the list is empty or not, is again a constant time step, because you only need to check for some very small conditions, and these conditions I am not enumerating because they depend from implementation to implementation, but it's very simple to figure out as to what these conditions are. Merge. So given pointers to the start and end, this is a basically O(n) step operation, because if you just want to say append one list to the another, then you only need to do a couple of pointer modifications and it will be done. So it's very easy to merge to linked lists. Splice, wherein you want to cut a linked list into 2 or more pieces. So given a pointer from where to splice, this is again a constant time operation. So some things which you would have noticed by now the lists are good at is insertion, deletion, or making arbitrary modifications in between the linked list. However, the penalty which one pays for all this is that you cannot do a random access in a linked list. So linked list is a simple data structure, and linked lists do not need a contiguous memory storage and hence can make efficient use of the available system memory. And this is the reason why in the Linux kernel, the network packets are stored in the form of a linked list. So whenever a new network packet comes through the network card, the kernel is going to basically allocate a small record for it, and that record is stored in the form of a linked list. The reason being that the network packets are always processed in order, so in order in which they are received, and you would not want to do a random access on the network packets. And also the kernel wants to make efficient use of the available memory. So this is one of the good places or where the linked list is used. There are of course several other examples. Large graphs are represented, as we will see later on, and many more. But this is one of the simplest examples to list out. Coming back to the gotchas or limitations of linked list, one thing which you need to keep in mind is that there is no find n operation in the list, where n is the index of the element. So what find n is going to do is it's going to return you the nth element. So you might implement the find n operation yourself, but what you will end up doing is traverse the list from the beginning or the end if it's a doubly linked list. And then it is going to be expensive. It will no longer be a constant time lookup. The cost of size or the length of the list, that particular operation is implementation specific and should not be used frequently. What we are trying to say here is don't make any assumptions about the size operation being implemented efficiently on the platform or the library which you are using for a particular platform. Rather, if you need to have the size operation used frequently, maybe a small amount of bookkeeping on your side is the safest way possible. Of course, until unless the library documentation by itself says that the size or the length operation has been implemented efficiently. So let's take a look at the C++ implementation of a linked list. Since the linked list is a fairly simple data structure, it's possible to implement it very easily in C++, and that is what is shown here. So we have the class cnode, which is used to represent each node in the linked list. And what we have done is the data element in this case, we have assumed it to be an integer. So what the constructor of cnode does is it actually creates a particular node and assigns the data to data, and the next pointer is set to be null. So of course, if we want to fix the next pointer, we have to do it ourselves. Then it also has a function getData, and getData is just going to return the data. And we have kept the data element as private and the next pointer as public. So note that the next pointer is of the types class node or C node, because it's going to point to a storage space which is similar to itself or is of the same type as C node. Then on top of this, we have another class CList, which is used to represent the entire linked list. So CList maintains two C node pointers, the start as well as the end. So this is not a very precise implementation of a singly linked list, because typically you will have no end pointer in case of a singly linked list. But just to make things simple, as well as have an operation which is similar to the STL implementation as you will see next, we have also maintained an endpoint. Two functions, pushback as well as getFront. So notice that they are not in the C++ coding convention style that we have been following, but what we have done is use these function names because they are similar to what STL does, so that there is no confusion and you will just find it very easy to correlate them to the STL functions. So what pushback is going to do is it is going to insert the data element data toward the, or rather at the end of the linked list. And getFront is what is going to return the first element. So here is the implementation of function pushback. What it does is C node pointer temp is equal to new C node. It is going to create a new C node, and then it passes the data value there so that the particular node is created, the constructor is here, and we can see how the data value will end up getting used. Then a small amount of bookkeeping, that if this is the first node, then basically the start as well as the end have to point to the same thing. And then you just return. In case it is not the first node, there is already a start node in the system, then end next is equal to temp, because what you want to say is that the last element is now the temp what we have created, and the end is equal to the temp element. So end is going to point to the last element. GetFront very simply returns the start get data, because start always points to the first element. So this is a trivial implementation of a linked list, and several functions such as insert, delete, splice we have not implemented here, as well as we have not done any kind of a bookkeeping to store the value of total number of elements in the linked list. But this is just here for the demonstration purpose. Another thing to note is that a proper class design will actually hide the class C node from the library user. So assuming if this is a library, you don't want to expose C node to the user, because he doesn't care about the individual node or how you are storing data. All what the user cares about is that I should be able to give you a particular type of data, as maybe just specify that create a linked list of integers or floats or something else, or maybe my class, create a linked list out of my class that I have created, and then go ahead and do all the operations on that. So this is what the STL library does, because everything is templatized inside STL. So we can just specify a particular type to STL and we will get the linked list.